Hello! My classmate Sarah Baalbaki and I, Marianne Khoury, are going to present today our project, which is about performance of computer systems. Today, we are going to discuss several topics about our subject. We're going to start by defining the performance. Then we're going to see what is the relative performance and the spec ratio. After that, we're going to define some terms like execution time, clock time, CPU, CPI, in order to understand how we calculate the performance of the computer system. Then we're going to study and see how we can improve the performance. So, what is performance? Usually, performance is known as how well a machine or a person perform a certain job or task based on several criteria. It's a kind of evaluation report of an accomplished task assigned for achieving a goal already set. So, what is performance in computer science? In computer science, performance is the amount of useful work accomplished by a computer system compared to the time and resources used. Better performance means more work accomplished in a shorter time and or using less resources. What about computer performance? The computer user is interested in the response time or execution time, whereas the manager of data processing center is interested in the throughput. The response time is the time between the start and the completion of a task in time units, and the throughput is the total amount of tasks done in a given time period, a number of tasks per unit of time. To really understand what the response time and the throughput are, I'm going to give an example of a boat assembly factory. When we say that we need 8 hours to produce a boat, it's a response time statement. Whereas 11 boats are produced per an hour, it's a throughput statement. In general, there is no relationship between those two metrics. Since they're not related, to get the best performance, the computer user wants response time to decrease, while the manager wants throughput increased. Now, the main factors that influence the performance of the computer system are processor and memory, input-output controllers and peripherals, compilers, and finally operating system. Relative performance. As we can see here, N equals performance of A over performance of B equal execution time of B over execution time of A. We can say that A is n time faster than B. The index n is specific to only one characteristic wanted, hence it's relative to the goal set before. To make this idea clearer, we're going to take the example of two airplanes, the Boeing 747 and the Buck-Suit Concorde. In terms of speed, the Concorde is approximately 2 times faster than the 747. However, in terms of capacity of passengers, the 747 has 3.8 more capacity than the Concorde. Hence, depending on the characteristic required, we can say whether the performance is good or not. For example, if the goal is to reach New York from Paris in only 3 hours, the Concorde has the best performance. But if the goal is to get as many people as we can to New York, the 747 will be more suitable and will have the best performance. SPEC ratio. SPEC means Standard Performance Evaluation Corporation. The SPEC ratio, also called speed results, are expressed as the ratio of time required to execute the benchmark compared to a reference time, which is the execution time on a digital equipment. The SPEC ratios for a given machine can vary widely from benchmark to benchmark. SPEC ratio is given as the reference time over the execution time. From this slide on, we are going to give some definition in order to understand how we compute and calculated the performance of our computer systems. As we know, the performance equals 1 over execution time. And we have two types of execution time, the elapsed time and the CPU time. Elapsed time counts everything. Disk and memory accesses, input, output, everything. It is a useful number, but often not good for comparison purposes. That's why we opted and we will focus on the CPU execution time. CPU time or CPU execution time is the time between the start and the end of execution of a given program. This time accounts for the time CPU is computing the given program, including operating system routines executed on the program's behalf, and it does not include the time waiting for input output and running other programs. What are clock rate and clock time? Clock rate, also known as clock speed, it is the speed at which the microprocessor executes each instruction or each vibration of the clock. The CPU requires a fixed number of clock ticks to execute each instruction. So the faster the clock rate is, the faster the CPU will be. So the faster the instruction will be executed, hence the faster the device is. The unit of the clock rate is megahertz or gigahertz. And the clock time is equal to 1 over the clock rate. The clock time is the time for which a CPU was used to process instruction for a given job. What is CPU clock cycle? It is the amount of time between two pulses of an oscillator. In fact, it creates oscillations, generating clock signals to control the speed of a processor or the central processing unit. The more pulses per second we have, the less time between consecutive ones, hence the faster the processor is. As shown here in the figure, we can notice that a clock period is equivalent to a clock cycle. In addition, older computers and slower CPUs could execute only one instruction per clock cycles, but modern ones can now execute multiple ones. Instruction count. It is the number of instructions issued by the ISA, Instruction Set Architecture, needed to execute a program. It forms the basis for various performance aspects of the microprocessor, such as instructions per cycle or cycles per instruction. The IPC, instruction per cycle, is how many instructions are executed in one CPU clock cycle. The CPI will be defined in the next slide with more detail with my colleague Sarah Baalbaki.
Hi, this is Sarah Baalbaki, and I'm going to be continuing from where my colleague Marianne left off. We're now going to discuss the CPI, which is the cycles per instruction. It is also known as the clocks per instruction or the instruction path length. The CPI is a very important component in determining the performance of a certain CPU or processor. The CPI is defined as the number of clock cycles per instruction for a given execution of a program. However, instructions can be categorized, and so different categories of instructions, such as loading words, storing them, branches, or ALU operations, will have different CPIs. And so, a more meaningful and efficient measure of the CPI is to take the average number of cycles per instruction. And this will now take into consideration the CPU design and architecture and the different categories of instructions. The CPI is also affected by instruction-level parallelism and instruction complexity, since if we implement overlapping the execution of instructions or pipelining, we are able to reduce the CPI drastically. The IPC, or instructions per cycle, is known as the multiplicative inverse of the CPI. Now we're going to be giving some important formulas and some examples for each. We're going to start off with clock cycles. A clock cycle is measured by the instruction count times the cycles per instruction. For the example below, we will consider an implementation of a MIPS ISA with 500 MHz clock with the below categories for instructions, and each are given their own CPI and instruction count, and we have to determine the clock cycles. We know that the clock cycles are the instruction counts times the cycles per instruction. So we will take each category of instructions and multiply their cycles per instruction with their instruction count. An example for a load word, it has 3 cycles per instruction and 25 million instructions, and so the clock cycles for load word instruction will be 3 times 25 million. We do that for all the different categories of instructions, and so we will obtain that this has the clock cycles of 375 times 10 to the 6. Now we're going to be discussing the CPI and the IPC and giving an example for both. The CPI, or cycles per instruction, can be obtained by getting the clock cycle for a given program and dividing it by the instruction count. The IPC, which is the multiplicative inverse of the CPI, can be determined by using the formula 1 over CPI, or simply getting the instruction count and dividing it by the clock cycles for a program. In the example below, we're given the number of cycles and the frequency for different types of or different categories of instructions, and we are asked to find the CPI and the IPC. We are not given the instruction count here, and so for CPI, we simply multiply the clock cycles for the program for each different category of instructions with their frequency. We add them up all together and we will obtain 4.4 cycles per instruction. For the IPC, we can simply use the formula 1 over CPI and we will get 0.227 instructions per cycle. Now we're going to be discussing CPU time. CPU time can be determined by multiplying instruction count with the CPI with the clock cycle time, or by multiplying the instruction count with the CPI and dividing all that by the clock rate, seeing as the clock rate and the clock cycle time are inversely proportional. In the example below, we're given different categories of instructions, each with their cycles per instruction and their instruction count, and we're required to find the CPU time. The first thing that we should do is find the average CPI for the whole execution, and we do that by multiplying cycles per instruction times the instruction count for each category of instructions. We will obtain 3.94 cycles per instruction. After doing that, we are required to find the CPU time. The CPU time here can be determined by multiplying the instruction count by the CPI and dividing all that by the clock rate, which is given as 500 MHz. In the end, we will obtain a CPU time of 0.75 seconds. The MIPS rating. The original performance measure was the time needed to perform one individual instruction, such as a load word, an add, or a branch. The next performance measure was the average instruction time, and this was obtained by the relative frequency of instructions and the time needed to execute each. Since instruction sets were similar, this was a more accurate comparison. We also have another way of assessing execution time, which is the MIPS, million instructions per second. It is an older and obsolete measure of a computer's speed and power, and it roughly measures the number of machine instructions that a computer can execute in 1 second. And so it can be obtained by getting the instruction count and dividing it by the CPU time times 10 to the 6, or by getting the clock rate and dividing that by the CPI times 10 to the 6. However, using the MIPS rating as a performance measure is not as efficient as other measures. This is because different instructions can take more or less time than other instructions. The MIPS rating of a program also only refers to the CPU speed and does not take into account the input or output timing. It is also difficult to compare computers with different instruction sets, seeing as MIPS can vary inversely with performance and between the same computer programs. Here we summarize the most important components in determining the performance of a certain CPU or processor. We have the CPU time, the CPI, and the clock cycles. And so, performance depends mostly on CPI, which is the cycles per instruction, and the instruction count, which are affected by the algorithm, the programming language being used, the compiler that the computer has, and the instruction set architecture. We can improve performance by increasing the clock rate. And we can do that by improving the instruction count memory. By doing so, the logical circuit is executed faster. A faster execution means a reduced execution time, which will lead to decreasing the clock time, and so the clock rate, which is the inverse of clock time, will increase. Another way we can improve performance is by reducing clock cycles, and we can do that by implementing or using pipelining. MIPS instruction execution can be divided into 5 main steps: instruction fetch, instruction decode, execution of the instruction, memory access for loading and storing words, and write back register for ALU and load word instructions. If we were to follow a sequential execution for these above steps, we would have a large number of clock cycles. In the example below, we're given an execution of a certain load word instruction, and it takes 8 nanoseconds to complete. Since we are seeing that the instruction fetch needs 2 nanoseconds, the register read needs 1, the ALU needs 2, data access needs 2, and the register write back will take 1. And so, each time we load a word, it will take us 8 nanoseconds to complete. However, if we implemented pipelining in the example above, we would be able to execute 2 or more instructions simultaneously, and so the number of overall clock cycles needed would decrease, since more than one instruction is being performed during one clock cycle. In the example above, if we were to follow sequential execution for the steps and perform 3 consecutive load words, it would take a total of 24 nanoseconds because each load word would need 8 nanoseconds for an execution time. However, in the example below, the total time needed to perform 3 consecutive load word instructions using pipelining takes only 13 nanoseconds compared to the 24 nanoseconds as before. This is because while one part of the processor is performing an ALU operation for the first load word instruction, another part is performing a register read for the second load word instruction, and another part is performing an instruction fetch for the third load word instruction. These 3 performances, an ALU operation, a register read, and an instruction fetch, are all performed at the same time during the same clock cycle, however they are for 3 different consecutive instructions. With this, we conclude our presentation on the performance of computer systems. Thank you for listening, and we hope you enjoyed it and benefited from it.